Okay, let's take one more look at solving a system of inequalities. We'll start as we have before, so I'm starting with the first inequality, and I'm trying to find the x and y intercepts. So if x is equal to 0, then we get 2y equals 6, and so y would equal 3. And so we'll have the point 0, 3. Let's see, if we let y equal 0, then we'll have negative x equals 6, and so x will equal negative 6. So we have the point negative 6, 0. Let's go ahead and graph this. We can get started on that. So we have one point at 0, 3, and we have our second point at negative 6, 0. And we can connect these with a straight, solid line because we have a greater than or equal to inequality. Since we're here, let's go ahead and test a point. So I'm going to test the origin since 0, 0 is not on the line. So I have negative 0 plus 0 greater than or equal to 6, and that is false. So our solution set will be pointing away from the origin for this blue line. So anything on the other side of the line that's away from the origin. So now let's go ahead and do our second inequality. So 3x plus 2y less than or equal to negative 2. So now I'm going to test x equals 0, and so we'll get 2y equals negative 2, so y would equal negative 1. So we have a point at 0, negative 1. And if y is equal to 0, then we get 3x equals negative 2, and so x would equal negative 2/3. Negative 2/3 is going to be just a little bit shy of negative 1. So let's go ahead and graph this. We have a point at negative 2/3, 0, and we have another point at 0, negative 1. So we can connect these together with a straight, solid line. Okay, roughly like that. And let's see, we'll go ahead and test a point. Again, the origin is not on this line, so we can go ahead and test the origin. So let's see, we'd have 0 plus 0 is less than or equal to negative 2. And that is, let's see, false. 0 is not less than negative 2. Negative 2 is less than 0. So this is false, so we would like our solution set to be pointing away from the origin. So we're pointing away. So we get some overlap with our original solution set. We've got one more inequality to consider, and that's y greater than or equal to 0. That means that we're going to have everything above the x-axis, or equal to the x-axis, but it has to be greater than or equal to the x-axis. Okay? So this leaves us with a feasible region that is unbounded. So all three of our feasible regions intersect over in this unbounded region between the green, the blue, and the red lines. But notice that the region never stops, right? It keeps going, over to the left, and it keeps getting taller, so it never stops. So this is an example of what we call an unbounded feasible region. It just means that the feasible region is not a nice contained region. It's unbounded and it keeps going in one or more directions. Notice that we do have corner points on this region. We would have a corner point at negative 6, 0, and we'd also have a corner point at this intersection of the green and the blue lines. Okay, so corner points are going to become very important in the next section. So just notice that there are corner points even if we have an unbounded feasible region.